OCR A, A-level physics. This is my second video on gravity and astrophysics, and this is about gravitational potential. Okay, so gravitational potential energy to start with. So the gravitational potential energy of a body is the energy it possesses due to its position in a gravitational field. So if you look at these kiddies on the climbing wall, the one at the top has more gravitational potential energy because she is higher up compared to the other ones. Okay, that's gravitational potential energy measured in joules. Now, this is all very GCSE so far, but don't worry. If you lift something, then you're doing work against gravity and the object gains gravitational potential energy. If you let go of it, then it falls and gravity does work and it loses gravitational potential energy. And in a uniform field, work is force times distance. So that's the force would be mg and the distance is the change in height. So the change in gravitational potential energy is mg delta h. So delta h, because it's the change in height, we can work out the change in gravitational potential energy. Now, a couple of questions though. What about if it's a non-uniform field? You know, what value of little g do we use? We can't use 9.81 because it changes in a non-uniform field. And also, where would a mass have zero potential energy? Is it on the floor? Well, no. On a universal scale, that's ridiculous. So that's what the kind of questions that we're going to be answering in this video. Now, one way we could find the work done would be the area of a force distance graph. So force against distance, if the force is constant, then force distance is just a rectangle. But in a non-uniform field, force against distance isn't. Yeah, it follows an inverse square law. So the area is the area under this curve. So how do you find the work as the area under the curve? Well, a little bit tricky counting squares. Maybe you could integrate. There's another way of doing it, and that's to use this thing here, gravitational potential. Not potential energy, potential, gravitational potential. Now, what do I mean? Well, it's the property of a point. The gravitational potential at a point is how much gravitational potential energy 1 kilogram would have at that point. That's not the official definition. We'll do that later on, but this is our working definition at the moment. It's big V and it's in joules per kilogram, and it's how much potential energy a kilogram would have at that point. So how much gravitational potential energy would a kilogram have at the surface of the Earth? And it's not zero, it is minus 62.5 times 10 to the 6 joules. So minus 62.5 million joules. That's how much potential energy a kilogram would have at the surface of the Earth. Yes? Why is it such a big number? And why is it negative? Well, because we say that a kilogram would have zero potential energy, not at the surface of the Earth, but at infinity. Where is infinity? It's an imaginary place which is an infinite distance away. It's very, very far away where there is no gravitational influence by anything. Yeah, the field strength is zero. So it's a very, very, very far away place, infinity. If you look at this diagram here, so it is sensible to say that a mass would have zero potential energy when it isn't in a gravitational field. So that's at infinity. So that means that the potential at infinity is zero, but it also means that the potential anywhere closer to the Earth isn't zero, but it's negative, because you would have to do work to get to infinity then the potential closer to the Earth must be a negative quantity. And in fact, how much work would you have to do to get a kilogram from the surface of the Earth to infinity? And it's 62.5 megajoules. So the potential at the surface of the Earth is minus 62.5 megajoules per kilogram. Yeah? To get 1 kilogram from the surface of the Earth to infinity, you would have to do a lot of work. Okay, so 1 kilogram has 62.5 megajoules less potential energy at the surface of the Earth than it does at infinity. So the potential at the surface of the Earth is minus 62.5 megajoules per kilogram. This is a tricky topic, really. Once you get your head around it, you realize it's not that bad. But when you first come across it, it's very, very new. And I understand that students have a bit of difficulty with it. Okay. This is our formal definition of gravitational potential. The gravitational potential at a point is the amount of work you would have to do to get a 1 kilogram mass from infinity to that point. Now that's a little bit weird. I've been saying the amount of work to get from that point to infinity. Well, the thing is, to get from that point to infinity would be a positive amount of work. To get from infinity to that point would be a negative amount of work. So that's why it's a negative quantity. It's from the definition of potential. It's because we're talking what we call a potential well. Yes, the mass of the Earth creates this potential well. Like if you imagine putting a bowling ball on a big rubber sheet, yes, it's a potential well. You have to do work to move away from the Earth. To calculate the potential at any point at a distance r from the center of a mass m, so gravitational potential is minus gm over r. Don't forget the minus sign, minus gm over r. Look at these graphs, and I've got a little job for you to do. I want you to list as many differences as you can between the two graphs. One of them is for little g, and one of them is for big V. So don't be lazy, pen and paper, list as many differences as you can. Okay, hopefully you've done that. So little g, notice it's positive and it's gm over r squared. So that's inverse square. V is negative, it's minus gm over r. So the shape of the graph is different. It's not inverse square, it's just inverse. If you at double the distance, it would be half as much. With little g at double the distance, it would be a quarter. Look at the units. Little g is newtons per kilogram. V is joules per kilogram. I reckon if you remember that potential is joules per kilogram, that's half the battle won. Electrical potential is joules per coulomb, isn't it? Yeah, joules per kilogram. At the surface of the Earth, little g is 9.81 newtons per kilogram. At the surface of the Earth, gravitational potential, V, is minus 62.5 times 10 to the 6 joules per kilogram. Here's a question for you to do. Okay, so pause the video, pen, paper, calculator, get it done, and the answer is... So the potential at that radius, minus gm over r, is that. And so the potential energy is basically joules per kilogram times by how many kilograms you've got. So it's m times the potential. So the GPE is minus 1.51 times 10 to the 10 joules. GPE, again, it's minus, potential is minus, so gravitational potential energy is also negative. Another couple of questions now. The satellite has a velocity of that. Calculate its kinetic energy and also calculate the total energy. So, kinetic energy is just a half mv squared. That's positive. The total energy, if you add them together, the GPE and the kinetic, you get this value. Note that it is still negative. The total energy is negative. And that means that our satellite can't escape. Yes, it's in orbit around the Earth. It can't bod off and do its own thing. It doesn't have enough energy to do that. That leads us to the next little thing, which is escape velocity. Imagine you threw a ball vertically upwards. How fast would it need to be travelling, ignoring air resistance? How fast would it need to be travelling to escape the Earth's gravitational field? And that's called the escape velocity. Yes, and we can work out an expression for that if we say that the kinetic energy goes to GPE. So a half mv squared goes to m delta v, and delta v, because it's getting to infinity where the potential is 0, then delta v is just the potential at the surface of the Earth. So a half, cancelling the little m's, a half v squared is gm over r. So our escape velocity is root 2 gm over r. Little job for you to do. Show that the Earth's escape velocity is about 11 kilometers per second. To do with escape velocity, now the average speed of air molecules at the surface of the Earth, I mean, if you've done the thermal physics, you will know, is about 500 meters per second at 20 degrees centigrade. Okay, that's the average speed of air molecules. Now, very few air molecules will have enough velocity to escape from the Earth. Some of them will, but a very, very small amount of them will have enough energy so that the Earth does lose a little bit of atmosphere into space, but our atmosphere replenishes itself due to kind of biological stuff going on, due to stuff coming out of volcanoes as well. So our atmosphere replenishes itself. If somebody had the brilliant idea of going up to the moon and releasing loads of air to kind of give the moon an atmosphere so that we could walk around on the moon, it wouldn't be able to hold on to that atmosphere for very long. Now, the escape velocity of the moon is like 2.4 kilometers per second, but it would lose a little bit of atmosphere every day, and then the sun would warm it up, and then it would lose a bit more, and then the next day it would lose a bit more, and then after maybe a few months, there'd be nothing left, and all of this atmosphere would have escaped into space. So would have a bit of a job terraforming the moon.